in inorganic chemistry and organic chemistry. So as we may know today, in fact, that's my first time to do video recording for my presentation. I hope it will be doing fine, and hope you guys will like that. And also, feel free to give me feedbacks after I come back. Okay, let's get started. Let's start with some simple concept: bronzed acid and the bronzed base. So we call bronzed acid if it can provide protons, and we call the bronzed base as a proton acceptor. So that means they can take up protons. So let's start with a simple example. And here, so let's use a very simple example. Okay, let's use hydronium ion react with ammonium, gave water and NH4 plus. So in this case, so we have hydronium ion as a proton donor, and that means it's a bronzed acid. Okay, in this reaction, so we know ammonium will accept protons, so we call it as a proton acceptor. So that's a proton acceptor. Okay, and also that's a bronzed base. Okay, so that's very simple. And another point that I would like to make is a proton cannot be exist by itself. It always associated with a base. Like in this case, it's the single proton is stick with a water. But in this case, the fourth proton stick with ammonium. Okay, right? That's what I'm trying to emphasize. All right. So the proton, can shuffle between two proton acceptors very quickly. So like in these two examples, and we have the proton, from here, move to water, and we get this hydronium ion, right? So this process it's in fact a highly reversible, dynamically highly reversible, and also the proton can go back to the fluoride. We can go to this direction. So the same thing for the reaction between the second reaction. So the proton shuffle between two bronzed base very quickly. So that's dynamic. So then you will say, as an example I showed before, you can say like the hydronium, after its lose proton become water, right? So hydronium is an acid, bronzed acid. After its lose proton become water. So water become what? Become a base, bronzed base. So in general speaking, when a proton donor lose proton, it will become a conjugate base. So same thing for base. When a base, after accept proton, it would become a bronzed acid. So let's also still use the same example to expand a little bit more. Okay, let's still use hydronium 3 plus ammonium 3 goes to water plus ammonium 4 plus. So in this case, so this one is an acid, we know, right? That's a bronzed acid. But after its lose proton, we get what? We form water, right? So that's become a conjugated bronzed base. Okay, same thing goes to ammonium. Okay, ammonium lose proton goes to ammonium. So this one is acid, and this one become this as a base. Okay, so that's conjugate acid and base. Okay, that's a pair. Always it's a pair. Okay. Then there are two simple reactions. So I hope you guys can practice these two reactions to figure out which one is bronze acid and which one is corresponding conjugate base, or which one is bronze base and which one is conjugate bronze acid. So there are two examples, very simple, and if you can have problem, so we can review that after I come back. Then let's talk about strengths for bronze acid or bronze base. So here, so that's a that's pH, right? So normally we use pH to that's a minus log of the activity of proton. So we use this to indicate the strength of acidity or basicity of aqueous solution. So for example, when pH equal to 7, we say it's neutral, right? So when pH less than 7, we call it acidic. When pH more than 7, sorry, let's greater than 7, so we call it L9 or basic. So that's the definition of pH. And also we can use acidity constant or basis constant to indicate the strength of base and strength of acids. So here, so that's a acidity constant. You can say that's a multiplication between hydronium ion with a conjugate base, okay, and divided by the concentration of unassociated HX. Okay, so here Kb is defined as hydroxide times the corresponding conjugate base, okay, conjugate acid, then divided by the concentration of B. Okay, so then if we use Nogan Ka, and we can get a P minus, okay, we can get a pKa value. So whenever you have a smaller pKa value, that means a strong acid. Okay, smaller means stronger acid. Okay, smaller pKa means stronger acid. Okay, so in contrast, when you get a bigger pKb, that means a stronger base. Okay, so let's show a table. So that's a summarized table for common bronze acid, and you can see here. So we have a very strong acid H iodide. It has minus 11 as pKa, right? So if you goes down with the increase the strength of the conjugate base like this one, okay, your pKa become larger, so that means become a weaker acid. So that's a table. So that's a table for common bronze acid and base. So you can see another you can see in this here, that's acid version. So here it's conjugate base. Okay, so there are a number of good examples. Okay, then let's also we talk about simple monoprotic acid. Also we have lots of polyprotic acid like sulfuric acid, H2SO4, all right, So also we have phosphoric acid, H3PO4, and for H3PO4, it can undergo stabilized, deprotonation. It can goes H2PO4, plus, and also further H2PO4 can goes to HPO4 2 plus, and HPO4 can goes further deprotonation can go to HPO4 3 plus, right? So this transformation really depends on the pH of your solution. Okay, so in this plot you can see initially, okay, at pH 0, at pK 0, so the phosphoric acid cannot undergo deprotonation unless you add base, like we add small amount of the potassium hydroxide. You will see by increased pH, this way, okay, this way, increase pH value by adding potassium hydroxide. So you will see the transformation of H3PO4 go to H2PO4. Okay, you will see that this purple line means the decreased concentration of H3PO4 with increase of potassium hydroxide. And as you keep increase the pH value by adding more potassium hydroxide, you will see the more formation of H2PO4. And also, after you overcome the pH value here, you will see start decrease of the H2PO4 minus, and you will see the formation of more the third species, the mono protic HPO4 2 minus. And when you increase up to pH up to 12.7, almost 7, okay, you will start to see more the final one, the fully deprotonated PO4 3 minus. Okay, that's a whole transformation. Okay, let's move on. Let's talk about a broad concept about Lewis acid and acidity and basicity. So we call it Lewis acid and Lewis basicity. So Lewis acid is a chemical or substance that can take up electron pair, a pair of electron, can give, okay, and that should be donor. That's right, should be donor. And here should be Lewis base should be, oh, that's right. Let's clean up, that's right. So yeah. So acid, so is a electron acceptor, okay, can take up a pair of electron. And Lewis base is a electron donor, okay. So we can use a MO diagram to accept what's Lewis acid and what is Lewis base. So in this case, that's Lewis. That's here. That's Lewis acid. Okay. ACID. Here, that's Lewis base. So you can see for Lewis acid, it has an empty. It has an empty normal orbital, so it's ready to accept electrons. And in on the other side, Lewis base, okay, it has a HOMO with a filled pair electron. So when these two interact, the HOMO of Lewis base will donate electron to the LUMO of the Lewis acid, so we can have a Lewis acid bonding interaction here, okay? So that's a interaction between a Lewis acid and Lewis